Okay, so good evening, everyone. My name is Shubham Rai, and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. Hope you are able to hear me. And today we are going to start week 11. We are going to discuss some problems related to week 11 lectures. So let me start. So in week 11, you would have studied related to energy methods. Let me see whether my mic is working or not. Yeah, it's fine. So you would have studied related to energy methods. So let me write that. So you would have studied related to energy methods. Right? In the energy method also you would have studied reciprocal theorem or reciprocal relation. In reciprocal relation, what was reciprocal relation? So it says that it allows us to obtain relationship between influence coefficients, right? Between influence coefficients. I'm just recapitulating and I'll only be writing formulas here. If you want detailed derivation, you can go back to lectures, watch those lectures. This session is mainly concerned with solving numerical problems. Okay. So it allows us to obtain relationship between influence coefficients. That is, we obtain relationship between Kij and Kji using reciprocal relations. Yes, so we can write energy stored in a body will be. So what will be the energy stored? So if F is force acting, F1 is the force acting on the body and delta 1 is the corresponding displacement. So energy stored in the body will be half into F1 into delta 1. Now delta 1 is the corresponding displacement or deflection. We can say that this is deflection or displacement, right? So we can also write as F1 can be written as K11 into delta 1. Sorry, delta 1 can be written as K11 into F1, where K11 is the influence coefficient. So we can just write K11 into F1 squared. Okay, because delta 1 is K11 into F1. And K11 here is influence coefficient. Influence coefficient. Right. Then you would have studied related to Maxwell-Betti-Rayleigh reciprocal theorem. So I'm just writing here. Maxwell-Betti-Rayleigh reciprocal theorem. What was this theorem? Do you remember? Can you recall this theorem? Okay. So this theorem says that if you have a force Fi, and due to this force Fi, you have displacement delta I. Okay. And you have another set of forces Fi prime, and due to that you have displacement delta I prime. So it says that this relation holds as per Maxwell-Betty-Rayleigh reciprocal theorem. So it says that work done by forces in situation 1 to the corresponding displacements of situation 2. So this will be equal to work done by forces in situation 2 and displacements in situation 1 to the corresponding displacements in situation 1. Okay. So, and it's very easy to prove this. You can go back to lectures. The proof is very easy. So corresponding displacement. So can you tell me what is corresponding displacement if you are able to recall? The corresponding displacement is the displacement acting and displacement at the point where force is acting and in the direction of force only. Okay. So it is the displacement corresponding to that force at the point on which the force is acting and in the same direction as the force is acting. Okay. So now Sir had derived different relations for different energies of the cross sections. So when a cross section is subjected to, let's say, extension or stretching, then it has different form of energy. I mean, form is same, but it has some formula. When it is subjected to bending, so it has some formula of energy, cross-sectional energy. When it is subjected to twisting, it has another formula. When it is subjected to shearing, then it has another formula. So I'm just going to write it down. I'm just going to write down all the formulas. So let me just write. We say that in a cross section, energy due to extension or stretching is given by E of that will be given by P square over EA, right? So this is the formula for energy of cross section subjected to stretching. Now P, I'm going to write what is the meaning of these terms. So P is external load applied to the body and this is area of cross section. And this is Young's modulus. Now you have energy due to bending. Okay, so energy due to bending will be given by mz square over 2 ei zz. Just verify. Should be p square over 2 e. I think this will be p square over 2 e. Please verify whether it will be 2 or not. I think it is p square over 2 ea. Okay. Then energy due to twisting. So these all are cross-sectional energies. The cross-section, and if you want to corresponding to a beam, these all are cross-sectional energies. If you want to obtain total energy, you'll have to integrate these expressions along the length. Okay. So energy due to twisting. Energy due to twisting like that. E of twisting. So that is given by t square over 2 gj. G is shear modulus of elasticity. J is polar moment of area. Okay, and here in this case, I is second moment of area, M is the moment applied on the beam. Now you have energy due to shearing. Okay. So that is given by E of shearing. So that is given by V square. V is the shear force acting on that cross section, average shear force. 2 divided by 2, and this is Ks is shear correction factor, and then shear modulus of elasticity, and then area of the cross section. Okay. So we can say that so total energy stored in the body. Let me just. So total energy stored in the beam, you can say, because we are talking about beam. Total energy stored in the beam in the general case is given by, so I'm just writing, I'm just summing all the energies, and you can only sum these energies when these forces do not have, these forces are in principal direction or they are mutually perpendicular to each other. So let's say twisting and mz are mutually perpendicular, shear force is also mutually perpendicular. Then you can add those forces, because the energy is quadratic in forces. You cannot apply superposition principle, right? But you are able to add when they are in principal direction, um, because when you will do vector product, so when they are perpendicular to each other or when they are uh, in principal direction, okay, so then only then it will automatically be squared and square and addition. I mean, in principal direction, it will get automatically added up. Okay, if you do a vector product of stresses and strains that are perpendicular and that are present. So let's say you apply, so let's say you have a beam and you apply forces perpendicular, force, torque, and moment perpendicular to each other. And now you try to write down the stresses in the body. So stresses due to twisting and shear and bending, and those will also be perpendicular to each other. So if you will do dot product of stresses and strains, there will be direct addition. Okay, so you will not have coupling between the components of these three forces when they are perpendicular to each other. So when they are not perpendicular or when they are not in principal direction, so you will have some interaction terms also, a coupling between, let's say, torque and bend, torque and moment and shear force, like that. Anyway, so this formula which I'm writing is only valid when you are applying forces, torques, and moments in principal direction. 0 to L, and principal directions are perpendicular to each other. 0 to L, P of x to the whole square over 2EA plus P of x I have written because P can be a function of x. So 2EIZZ, and this adding all the energies, cross-sectional energies, plus M, you have My and Mz, right? You cannot have Mx because that will be twisting. Okay, so that will be included in twisting. So that I'm writing here T of x the whole square and 2GJ, plus you can have Vy, that will be shear force over 2 of shear correction factor over Ga plus V of z. You cannot have V of x because V of x is the force in x direction, let's say, that will come in axial force, and that is taken care here in P of x. To KGA. K is again its shear correction factor. And if you integrate across along the length of the beam, you will get the total energy. Well, let's solve some problems. So let me just write. Let's say we have problem 1. So what you have to do is you have to think of a rectangular beam as shown below. I'll draw the diagram, don't worry. So beam is rectangular in nature. I mean, it's kind of rectangle, and its cross section is circular. Okay, so you have to assume its cross section to be solid, circular. Now you have to suppose the ring is subjected to equal and opposite forces equal and opposite forces at A and B. Okay. And now what you have to do is you have to neglect energy in beams per section. You have to due to shear force and axial force. So due to shear force and axial force, you have to neglect the energy in beams per section. So you only have to take energy due to bending. Okay. So let me draw the diagram. How does the beam look like? So it looks like this. Let's say hmm, so this is the beam. This is not the cross section. This is the beam itself. Cross section is circular. So cross section will be something like this. Here it will be circular. Okay. So let me just show. So here you have, let's say, 4 points. I'm naming these 4 points as, let's say, this is A, um, this is B, this is C, and this is D. Okay, and two forces are acting. This force is here. You can see force is acting, which is P, and here also force is acting, which is P. Okay, and of course the thickness. I mean, here it will be 2R because the section is circular. R will be the radius of the cross section. So total thickness of the cross section from the center will be 2R. A few more dimensions are given. So this dimension here is H, and this length here is L. This is L. Okay. Now what you have to find, so you have to find by how much will point A and point B, you can say A and B, yeah. By how much point A and point B get closer to each other. Second, by how much will points C and D get farther apart, right? So third one is you have to find what is internal moment in the cross section at C. So these three things we need to find out. Okay. So firstly, you have to find out by how much will point A and B get closer to each other. Second, by how much will point C and D get farther apart. And third, you have to find what is the internal moment in cross section at C. So can you imagine? So let me start with solution. So can you imagine how this beam will look like after deformation? So let's say we had a beam like this. After deformation, how it's going to look like? So since you are applying load at this point here at the center and this point here at the center, so it's going to look something like this, right? So from here it's going to bend. And here also going to bend. And then here also it's going to bend. So it's going to look something like this, right? For deformation. So this will be the deflection here, this will be deflection here, and this will be deflection here, and this will be deflection here. And points are this is point A, this is point B, this is point C, and this is point D. And this is load applied P into, right? Okay. So this will be the shape of the deformation, but we are going to assume small deformation theory. And we are going to take small deformation theory. So your strain displacement relationships are linear. The material is also linear elastic. Okay. So let me just start the solution. So how will you start solving it? So firstly, we'll try to find out axial force in the cross section. So let me just draw this diagram here. So if I draw a diagram like this, you have to use a lot of free body diagrams. It's a very interesting question. It may look like that it's very difficult, but you will see that how easily we will solve this question. Let's say we draw this diagram, and since load is applied here is P. Okay. And so the force is acting. So let's say that I have got the cross section from here. I mean, this is C. Let's say this point is C and this point is D. Okay, originally. So let's say this point is C, this point is D. So obviously, to balance this force P, there will be further forces acting on C and D. So let's say that these forces are there, right? So you have forces at C and D. And what will be these forces? So let's say if you will do the force balance, so F1 plus F2 will be P, and then you can do moment balance also. So finally, these two forces will be equal. From the symmetry, these two forces will be equal, and their magnitude will be P by 2 and P by 2. So we say that, let's call it as FC. I'm calling these forces as FC. So FC is P by 2 here, and here also FC is P by 2. Although it should be FC and FT but these 2 points are symmetrical, so I'm just calling it as FC. Okay. Now there is one more thing, let's say I want to find the shear force at this point. So let's say this is VC, shear force in this direction. I just want to find out that. Let's say here there is some shear force, and later on in the third part we need to find out internal moment in this cross section also. So how we are going to find out the shear force? Can anyone tell me? So there would be shear force as well as moment here. Here there would be moment also, that's called as MC. Okay. So if you balance the force again, so if there is VC here, there should be VC here as well in the negative direction, right? Because then only horizontal forces will get balanced. And if you balance the moment, so let's say you take this point D, and from this point, if you try to balance the moment, so it will be P into L by 2 and minus this P by 2 into L. So these two will get cancelled, moment due to these two forces. Then you have due to VC, it will be 0, and due to MC, there will be moment MC. So if there is net moment MC, so there should be one more moment in opposite direction that should be acting here. So MC will act here as well. Hope you have understood. So this is the scenario. Now you need to find VC and MC. So VC can be, so you are able to see that there is a bending of this beam here, there is a bending. So now we are at the central point. So if you imagine, if you are able to imagine, the central element of this beam will not get sheared. So shear is change in angle between the sides of a small element. So if you take small element here, so there can be change in angle because related to, let's say, bottommost side, the right hand side is going downward, so there can be change in angle. But if you take an element here, so here the change in angle will not be there because the topmost side will also be going downward, and the rightmost side will also try to go downward, and there will be some bending like this. So the net change in angle will be 0. There is one way of looking at this, is one way of looking at it, that VC will be 0. Another way of looking at it is, um, let's try to find out the moment along this length. And you know this formula, in bending we derived this formula that V is dm by dx. I mean, sometimes it is written as minus of dm by dx, but we can conclude from here that if there is no change in moment along a length, so shear force at that point will be 0. So let's see whether there is change in moment along this length or not. So let's say we are standing here and we move to this point. Let's say initially we are at this point and we have moved now to this new point. Okay, we have moved to this point now. Initially we were here. So at this point, net moment was 0. Now let's see at what happens at this point. So at this point, you get moment from VC. So VC will be moment from VC will be VC into this height, and then it will get cancelled with this VC because it is in opposite direction, and the distance of the line of action of force and this point is same. So due to VC, the moment is 0 here, and due to MC also, this is acting in this direction and this is acting in the opposite direction. Due to MC also, moment will be 0 here. And let's see about, so due to P, so due to P, this will be P into L by 2 in the in anti-clockwise direction, and due to P by 2, so it will be due to P, it will be P into L by 2, and due to P by 2, it will be P by 2 into L. So these two also will get cancelled. Moment due to these two will also get cancelled. So net moment again will be 0. So it means moment is not changing along this length. Okay, I'm talking about net moment. There will be moment actually at this net external moment will be 0. Okay, you can see that there will be moment along the cross section. What I'm saying is, if you make this way, I think I have committed some mistake in interpretation. So let's say instead of going here, you go up to here. Go up to here only, okay? So if you do that, let's see what is the moment. Okay, yeah. So then I think this point will not come into picture. So all the forces here won't be considered. I'm sorry, I have done wrong interpretation. So net moment obviously will be 0 because this body is in static equilibrium. So there has to be, I mean, net moment should be 0. So net moment at this point 0 implies that this body is in static equilibrium. Anyway, but we have to prove that the moment, bending moment acting in this cross section, that is not varying. So here if it is MC, here also it should be MC. Well, let's see that. Okay, so again here there is P. I'm just trying to see whether we can prove by this method that VC will be zero. Otherwise, we will resort to first method that I've explained, that this element, small element here, the sides of the element will, the angle between the sides of this element will not change because it is going, I mean, you can imagine that it is a central point and this side is also going down and this side is also going down. So there will not be any change in net angle of the sides. If we take a small element here, take a small element like this here, the sides of this small element is not going to change. Anyway, let me derive through this method. So as we see here, this is point D, and this is MC here, and this is P by 2 FC. This is now about this point. At this point, I try to find out. So moment due to P will be zero because P is acting in this direction, and this is P into L by 2, and this is P by 2 into L, and both are in opposite directions. So moment due to P will be zero. Now here there will be one moment acting, that is again okay. So now due to VC, it will be VC into this length, and that will be in the same direction as MC. So it will be, let's say this distance is X, so it will be MC plus VC into X. Okay. So from this analogy, you cannot say that your moment will be MC only. It has a component VC into X. Anyway, but yeah, so from first analogy only, you can say that VC will be zero. So you can post on the YouTube, in the YouTube comment box, if you find any other method to prove VC equal to zero. Anyway, so now this VC will be zero, so that's why now here the force, the moment will also be MC throughout this cross section. Anyway, so we will apply Cauchy-Lerner theorem here to solve this question. So while applying Cauchy-Lerner theorem, we will assume that there is a dummy force VC acting, and later on we will substitute it equal to zero to get the displacements. So right now I just want to take this part here. If I draw this part, so here at this point the slope of the beam will be zero, and so it will be something like this. So we draw this in two parts. One part is here and one part is like this, and I assume that so this green part will look something like this, right? It's looking something like this. So this part is this one going from here to here, and the next part is this one up to C. So I have shown fixed here because it is something like fixed because slope here is zero, and I have taken this as reference position. So deflection again, all there is a deflection, but I have taken this as a reference. So deflection, some I can say here is zero, and subsequently deflection is increasing up to here. So I've just drawn this shape, but since the deformation is very small, so there will be a small difference between this shape and this shape here. So I'm just writing here. So this is point A, this is point C, and there will be the forces acting will be, so VC will be acting here. That will be shear force, and so that will be zero. And here there will be FC acting. So that will be P by 2. And not talking about MC, we will determine MC later on. Now I'm going to divide this into two parts. One is this length and one is the horizontal length. So if I talk about the vertical length, so let me just write. If I talk about the vertical length, so in vertical length, let's say I am at this point, which is at a distance x from point C. And at this point x, I want to write the bending moment. So you know that here at point C, there will be VC acting. Here there will be FC acting. Right? And MC is also acting. So I'm just writing MC here. MC is also acting. And VC, we know that VC is equal to 0. And we are at distance x. So I'm just talking about this horizontal length. So horizontal length, sorry, vertical length. So vertical length had a height of h. So this will be h by 2 and this one will be L by 2. Anyway, so if I just write this part of the beam, if I draw this part of the beam, so it will be something like this. And let's say this is point x, and this is here we have VC, here we have FC, and here we have MC. Similarly, at this point, which is this point which is at a distance x, so there will be mx in opposite direction, and there will be shear force. There could be shear force as well, right? And there can be axial force as well. But I just want to write mx, so I need not to worry about other, because we only need to take energy contribution due to bending moment. We have to neglect energy contribution due to shear force and axial forces. So I only need to write moment at any cross section, at any point in the cross section. So and using that moment, I'll write the energy corresponding to bending moment. Okay, so this is the diagram for the vertical part of the beam. So if I write mx for the vertical part, so let me just write. Here we have vertical part, and if I write mx, so mx will be how much? So it will be mc plus vc into x, right? Because mc will introduce moment in positive z direction, right? And vc will also introduce moment in positive z direction, so that's why mx will be in negative z direction. And that will be equal to mc is equal to vc into x. Mc is equal to vc plus x, right? Is this fine? So you could write equilibrium equation also, because this is in negative z direction. This will be minus mx, and this will be positive z direction. So plus mc, and this will be also positive z direction. So plus vc into x. So from there you can derive this formula. Now coming on to the horizontal part of the beam. So horizontal part will look like something like the same diagram. So horizontal part will be here. So let's say we are here, and this part is at a distance x from here. Now at this point we have VC and we have FC and we have MC as bending moment, and VC obviously is 0. So if I just draw this part of the beam, so this part will look something like this, right? Sorry. So if you draw the free body diagram now, so here let's say you have shear force acting in this direction and axial force acting in this direction and moment acting in this direction, but we are only concerned with finding moment, because we only have to write the energy due to bending moment. And so here we have MC acting, and here we have FC also, which is better. Now if you try to do the force balance of the horizontal part, If you do that, so finally, what will you get? So let me just write it this time. So mx is in negative x, negative z direction. I mean, it is pointing towards the plane, into the plane, and it will be mc and plus fc into x, right? So that will be 0. Okay, and then we have vc also. So we will take contribution due to vc. Later on, we will put vc equal to 0. So due to vc also, it will be in plus that direction. So plus vc into L by 2. Because this length here is L by 2. Sorry, it is h by 2. So I should write h by 2. Okay. So this length here is h by 2. So now let me write total energy due to bending. So you can say that total energy due to bendings, and I'm just writing at any point on the cross section. So firstly, um, we'll have to write for the vertical part and then for the horizontal part. So I can just write E, which is a function of Fc and force at axial force at C and shear force at C and bending moment at C. So that will be firstly the vertical part. So that will go from 0 to h by 2. And the cross-sectional energy is mx whole square, mx, which is mc plus vc into x, right? It is m square over 2ei, right? 2ei in dx. Then you have to go from 0 to L by 2, and I'm going 0 to L by 2 because I'm starting x from here. Okay, I'm starting x from here. In this case, I'm starting x from here, and in this case, I'm starting x from here. So I'm going from 0 to L by 2, and energy is again mx square, but the expression of mx is different now. The expression of mx is um, from this equation. Obviously, this equation has to be equated to 0, right? So from this equation, so this from this equation, mx will be how much? So that will be mc plus fc into x plus vc into h by 2. So I'm just writing here the expression of mx. So that will be mc plus c into x plus. And please do not think that we have taken contribution due to axial forces. I mean energy due to axial forces and shear forces. No, because this is the whole and solve bending moment. And here you can question that here VC is coming, FC is coming, and because these are contributing to the bending moment. If we had to write the explicit expressions for the shear force, explicit expressions corresponding to energies of the shear force and axial forces, so we would have written the shear force at any cross section at point X and the axial forces at any point in the cross section, let's say at point X. Then we would have added those energies in this expression. So it would have been Vx square over 2 Ga into shear action vector that we have written here. Yeah, here it would have been Vx square. So that would have been added to this expression for both horizontal and vertical parts of the beam. And here also we would have this signs. but we are not adding these two energies, so we are neglecting them. And we have only taken this part of the beam from here to here. We are adding energies from this part to this part, because once we know the energy of this part, we can just multiply by 4, because these every other part is symmetrical. So this part is symmetrical to this part, right? So these two will have same energies. So, and then this right half part is symmetrical to left half part. So once we have the energy of this part, we can have a total energy of the system. That's why we are doing it. Now, yeah. So remember that we have Vc equal to 0, that we will put later on. And Fc is equal to P by 2. So here we have Vc equal to 0 and Fc is equal to P by 2. As of now, Vc is dummy force, dummy shear force. Later on, we will put equal to 0. So now, what we need to find out the expression for MC, right? In the third part. So to find out that, we can say that at C, there will not be any rotation of the cross section, right? Because it is kind of, the beam is vertical and this part is also kind of tangent here is vertical. Okay. So there is no rotation of the cross section. So that's why theta x will be 0. So theta x, how we can find theta x? So we have to differentiate this energy with respect to MC, right? So we will get theta c, and then we will put equal to 0, and then we'll find the value of MC. So what we are saying is rotation at C will be 0. This implies del E by del MC, which is theta c, right? So that should be 0. This is by Castigliano theorem. You would have learned in the class, right? So if we do that, so let's differentiate E with respect to MC. So if you do that, so del E by del MC, if you differentiate, it will be 0 to h by 2. Since these limits are not function of MC, so we can go within the integral, so we can directly differentiate this. If this would have been, if the limits are a function of the variable which with respect to which you are differentiating, then you will have to apply something, Leibniz rule of integration. Okay. So you can go to Wikipedia and just search Leibniz rule of integration. So anyway, so you can directly differentiate. So if you differentiate, what will you get? You will get MC plus Vc into x over 2 2 will get cancelled, because and dx, and differentiation of MC with respect to MC will be 1, and then this part 0 to L by 2, right? And if you differentiate now, you will get MC plus FCX plus VC into H by 2 over EI into dx. And then in this expression, what you have to put is you have to substitute now, because you are evaluating this expression at x is equal to c, right? So for we, you know that you have to substitute at x equal to c. You have VC is 0 and FC is E by 2. If you put here, after differentiation, you have to put, if you put del by del C, del by del MC at x equal to C, which is again, so that is equal to theta C. So that will be, so VC will go to 0. So now you are left with MC over EI. MC is moment at C, which is constant. EI is also constant. It's not varying with x, because cross section, let's say, symmetrical, it is circular only. And so 0 to h by 2 and dx. So you will be left with here 0 to h by 2 and dx plus. If you now substitute, so you will get finally MC over EI 0 to L by 2 into dx plus FC is P by 2, so P by 2 EI x dx, right? And the last part will be 0 because VC will be 0. And 0 to L by 2. So if you do that, so you will get MC H by 2 EI plus MC L by 2 EI plus P L square by 8 EI, right? So this will be 16 or 8. Let me just see. If C will be P by 2 x square by 2, which is 4, it should be 8. Okay, yeah. So it should not be 8, it should be 16 because um, this is already P by 2 EI. And from here you'll get x square by 2. And now you're substituting 0 to L by 2. So you will get L square by 4 multiplied by 2 will be 8 and here 16. So finally, the expression for MC that you are getting is that you will get will be so, and obviously this should be equal to 0. So if you now take MC common, so you will get H plus L over 2 EI and plus PL square over, I mean, this will be equal to 0. So I can just directly write this will be equal to minus of P L square over 8 EI, right? So EI and EI will get cancelled. So MC you are getting as minus of PL square over H over 4H plus L. So it's 16, okay. Yeah, so over 8 H plus L, right? So finally you will get this. Now you have MC. So further you need to find first and second part. You have to find the deflection of point A and B and deflection of point C and D, and so and these two deflections will be equal if once you have point A, so you double that, so you'll get how much will point A and B get closer together. So once you have deflection of point C, you double that, and you'll get by how much will point C and D get farther apart. So let me do that. So finally, you can just write delta of CD will be equal to twice of delta of C, right? So how will you find delta of C? And that is the displacement at C. So that will be del E by del VC, because del is the corresponding displacement related to shear force. So you have to differentiate with respect to shear force at C. So let's do that. So if you so expression for E you already know. So if you do del E by del VC, that will be delta of C, and later on you have to put VC equal to 0. Right now VC is a dummy shear force. So if you do that, so finally you will get 0 to H by 2. If you differentiate, so you'll get MC plus VC into X, right? Over 2 EI, and then you differentiate VC into X, so that you so finally you'll get X. Plus in the next expression, it will be 0 to L by 2. So it will be MC plus square will go away. So MC plus VC into H by 2 plus FC into X divided by EI. 2 will go away actually because square was there. So finally it will be multiplied with H by 2 because VC into h by 2 will get differentiated again. So this will be h by 2, then dx. So you get this expression. Now in this expression, you have to put VC is equal to 0 and FC is equal to P by 2, and you have to integrate. So this will get delta C. Sorry, so you get delta C. Um, so that will be MC. Now you have the expression for MC. So MC into X. So MC over EI, and this will be X square by 2. And this will go from 0 to H by 2 plus VC over EI. And already you have X square, so it will be X3 by 3. And it will go from, I mean, anyway, this VC part will go 0 because VC is 0. So you don't need not to do that. So plus go to the next integral, so that will be MC over EI, and there's no, and then there is multiplication of h by 2 here, so I'm writing h by 2, and there's no x term, so dx integration of dx will be x, so simply you'll get L by 2 plus VC will go to 0, FC will go as P by 2, so it will be P by 2 EI, and you have h by 2 here, and then you have x term also, so x dx will be x square by 2, so this will be x square by 2, and this will go from 0 to L by 2, right? So finally what you will get, so you'll get MC over 8 EI, MC at square over 8 EI plus MC HL over 4 EI, this is L, plus P over how much EI it will be. So 3 4 8 32 EI, and H into L square. Finally we get this. Okay. I think this is fine. So you can do further simplification. So if you do simplification, but you can take MC terms common. So MC you can take common, then H you can take common, then I think you can take 4 common and EI common. To do that, so finally here you will get H by 2 plus L, right? And plus you have PL square H over 32 EI, right? So now you can put the value of MC. So MC is minus PL square over 8H plus L. So finally I'm putting here minus PL square over 8 H and H will get cancelled, so 8 for 32, so it will be 32 EI, and H plus L is also there, so here also we have H plus L. So H will be there or not? Yes, H will be there because there is no H in the denominator. So this will be there, and now you have H by 2 plus L and plus PL square H over 32 EI. Okay. So finally, you can take now P also common. So all the P terms. So let me see. So you can take minus of PL square H simply as common, and then 32 EI also as common. So finally, what you will get? So you will get this will be plus, so H plus 2L over 2 into H plus L. So that will be coming from here, and then this will be minus H. Okay. It is fine. Actually, this will be minus 1. Okay. Because you have taken h also to be common, so this will be minus 1. So you can simplify now. I think it has become very simple. So PL square h. So h plus 2l. So you'll get h plus 2l minus 2h minus 2l over twice into h plus l. Okay. So finally, what you can see is this L and L will get cancelled, and this 2h minus 2h will be plus h. So finally, what you are getting is PL square h square over 64 EI in h plus. That is your delta C. And delta CD will be twice of this. So this will be PL square h square over 32 EI. And this will be your delta CD. Finally, you have to find delta AB as well. So how will you find delta AB? So delta AB, similarly, we can say that the delta AB will be twice of delta A, and delta A is nothing but um, how will you find delta A? So okay. So actually, for finding delta A, we do not have. Do we have expression for P in M? Yeah. So we have actually we have written. We have considered this beam, right? We have written energy of this beam. And so it was easy to find the deflection at this point and equating theta c at this point equal to 0 because we have this beam here. We have this beam here. So one thing that you can do is, if you are able to see, so the vertical deflection of point C, okay, that will be equal to the vertical deflection of point A. Are you able to see that? I mean, we have taken this as reference, right? So in this as reference, the point C will be this time, I mean this much above, right? Otherwise it should be ideally C is not point C is not getting any vertical displacement because it is at its place. It's not getting um above or below, right? So it is just at its place. But since we have taken this as the configuration reference point, we have taken this as the origin. So we can say that the deflection effective deflection of point C will be the effective deflection of point A, right? Or you can also differentiate with respect to P, and then you will get in the energy expression. If you differentiate with respect to P, you will get the deflection at this point here. But we have set this point as free, and this point we have fixed. So that's why in this energy expression, let me just see. So if you differentiate with respect to, let's put f c is equal to p by 2, and if you differentiate with respect to p, so then also I think you can get, and later on uh but there you have to take x is equal to l, right? I mean this way. Yeah, but in that expression you will not be able to use the expression for vc because we have said that vc will be 0. So we want to use point c only. After differentiating, let's say you differentiate with respect to P, so you won't be at point C, rather you will be at point A. So we want to use point C only. Anyway, so with respect to, so we have taken this as origin. So that's why with respect to this origin, the deflection of point C will give deflection of point A. Ideally, C is not going any vertical deflection, but since we have taken this as the origin, there will be ideally there will be vertical deflection of point C. Okay, because otherwise it would have been this and this going downward. So C would have been here if it would not have been uh, if the origin was considered this, then C was here, and if the origin is considered this, then C should be here. But as per this configuration, it is going some deflection. Anyway, that will be equal to deflection at point A. So I mean, it's kind of virtual deflection. It's not a real deflection. It's just that we have taken the origin here. That's why the deflection at point C, there will be some deflection at point C because with respect to this origin, ideally C should be here in some undeformed configuration, because if we go from here, L by, I mean, this is how much? Yeah. So if we go L by 2 this side and H by 2 this side, so we'll reach somewhere here. But C actually is here. So there will be some deflection of C. And that will be the amount with which we have brought this point down, and that will be the deflection of A. So let's find the deflection of C in Y direction. So this was the deflection of C in X direction. We can say that. That's why we have differentiated with respect to force VCs, because VC is in X direction. Now we have to find the deflection of point C in Y direction. So we can say that deflection of C in Y direction, that should be equal to deflection of point A, and deflection of C in Y direction, that will be del E by del F C, you can say. Okay, because force is acting at point C. So if we differentiate with respect to FC, we will get deflection at point C. Okay, so let me just write the differentiation of energy with respect to FC. So del of Cy, because FC is acting in Y direction at point C. So that will be del E over del FC. And if you do that, what will you get? So finally you will get 0 to L by 2. And you need not to go, let me just, you need not to go, just wait a minute. Let me write the expression of energy again. What was our expression for energy? Then we will differentiate. So our expression for energy was, this was a function of FC, VC, and MC. Okay. So if this was 0 to H by 2. So in the first part, in the vertical part, it was MC into VC into MC plus VC into X to the whole square over 2VI into dx, plus the second part 0 to L, it was 0 to L by 2, and it was MC plus VC into H by 2 plus FC into X to the whole square divided by 2VI. And now you have to differentiate this with respect to FC. First part is not a function of FC, so it will go to 0. So second part will be there, so that will be 0 to L by 2. Because in the first part, in the vertical beam, FC will not introduce any bending moment because it is along the length of the beam. But in the second part, in the horizontal beam, FC will introduce bending moment, and we are only taking the energy due to bending. So Let's do the differentiation. Finally, you'll get x here and bx. Now, if you solve this, so now you have to put VC equal to 0 and FC is P by 2. And MC also you have the expression now. So um, finally, what will you get? So you'll get MC into X, MC over EI. And then you have X also, so X squared by 2, so means L squared by 4. And multiplied by 2, so that will be L squared by 8 plus VC by 2 EI into H. And then again you have L squared by 8, right? Plus you have FC over EI. FC is P by 2, we'll substitute that. And here you will get x cubed by 3. So 1 by 3 is already there. X cube will be L cube over 8. So this will be 1 over 24. L cube over 24. Okay. So now what you can do is you can substitute the value of FC and MC. So if you substitute MC, so that is PL square over um how much it was? Minus of PL square over 8 into H plus N. So that will be 8 times 8 64, and then L square will remain as it is EI and then H plus N plus VC will go to 0. So this term will be 0 because VC will be 0 and FC is P by 2. So we get PL cube over 48 EI. Yeah. So we can take some terms common. So if you take that, so you can take PL cube over 16 EI common, I think. And if you do that, so you'll get here you will be left with L, and here you will be left with 3 and H plus N. Sorry, 4. Yes, here you will be left with 1 over 3. Right. So finally, if you solve this, so you get, yeah, so even I think this will be minus. So if you solve this, you'll get 16 PL cube over 16 EI, and we take the LCM, so you'll get 12 into H plus L. And finally, you're getting here minus 3L, right? Plus you'll get 4 times H plus L. So finally, if you solve this, so you are getting PL cube over 16 EI and 4H minus 2L, right? So you can take 2 common from here, so will get cancelled. So how much you get? There's some mistake. Let me just see. This is fine. We'll Q if we take commons, we'll get minus 7 here and here and so by 3 4. So finally, I think this is fine. So So let me just say 48 minus plus 7 minus 3 and 4 minus plus. So you'll get 4h and minus 3l plus 2 minus 2l. Okay. Yeah. So can you tell me, so this is 4h and this 4l minus 3l, so that will be l plus l, right? So yeah, this is the answer, I think. I'm not wrong. If I'm not committed a mistake like this. 16 for the 64, and from here you can get L minus of 7. Okay, that is fine. It's 14. Yeah, so this is fine. This is the answer. So that's what you will get. So this will be del of C y. That will be del of A. And del of AB will be twice of del of A. Okay. So coming on to the next question. So question 2. So in question 2, what you have to do is you have to find using energy method, I mean the Castiglione theorem. You have to determine first part. What you have to do is you have to determine the vertical deflection of point B under the action of load W. I'll draw the diagram, don't worry. And in the second part, what you have to determine is you have to determine the horizontal reaction force at B. You have to find horizontal reaction force at B and vertical deflection at point B. And there is more information. So it is given that the end B is free to rotate, but it is free to rotate means there will not be any bending moment because there is no resistance to the bending. So, but can move only in vertical direction. So what you have to do is you have to consider all forms of energy. That is bending, twisting, and stretching. There will be three energies here, as well as shearing energies. Shearing energy. So here you have to consider all kind of energy. So let me draw the diagram. So diagram something looks like this. Draw a circle. So how do I do that? If we draw a complete circle, then we just okay, that's fine. Then what I will do is I have to cut it from here, cut it from here. So I can just put this one. And let's see, we have here you have some roller. Okay, let's try and roll that block. Yeah. So and so this is point from the center actually. Let me show clearly that this is center. So it's the center. So from this center you have this radius as A. This point is termed as C. This point is A, and this point is B. And this load is acting here, which is W. Okay. So since only vertical deflection is allowed here, and it can bend also. I mean, rotation is also allowed, but horizontal deflection is not allowed. It cannot move horizontally. So there will be only horizontal reaction here. Reaction will be horizontal. Since moment is allowed, so bending moment at this point will be zero, and vertical moment is allowed, so vertical reaction will be zero. All the vertical forces applied here. Now you have to find the vertical deflection of point B under the action of load W and the horizontal reaction at point B. So let me go for the solution. For solution, let me just copy this figure, paste it here. Okay. Hmm. Okay. Now I'm taking, so to write the energy of this body, I have to write all the forces at a particular point in the cross section. So let's say this point is located at an angle theta. So let's say it's located at, so this is circular cross section, circular body. So I'm just going in cylindrical coordinates. So let's say it is theta. So we know that at point B, uh, if we just trying to draw the free body diagram. So if we only keep this roller and this remove this, we only keep the roller. So there is a force W acting, and this RB reaction force will be acting, and then this moment will be acting. So this will be moment at B, and moment at B will be zero because rotation is allowed at point B. So moment will be zero, and this reaction force RB will be acting. At any point in this cross section, so let's say at any point which is at an angle theta, so you have this kind of geometry. So we can say that if I draw this section only, this section here, if I draw a zoomed version, so it will look something like this. right? And you get to here, right? So this will be something like cross section, and so the angle is theta. We have this angle is theta. So I'm just writing the forces again. This will be RB. This will be W, and this will be how much? This will be MB, which is 0. Right? Now at this point you need to find, so at this point you need to find, let's say, f of theta, and here you need to find m of theta and also the shear force. So let's say this is v of theta. Okay, so the directions, okay, anyway, so the directions which I have shown here, I'm taking those directions as positive. So how will you write the forces? And you just have to write equilibrium equations. So obviously this n theta is in pointing towards a positive z direction, so that will be positive. We can take as positive. This, I mean, this you can take negative, and then the this force here, that depends whether you take positive or negative. So toward the center, so at a cross section having plane normal as e theta, and the shear force pointing towards the center, so that will, you can take positive or negative, whatever you want to take. Let's say I take this as positive, and let's say I take this as negative if I want to take that way. Okay, so let me just resolve everything in xy coordinates. So how will you write all these forces? So I'm just drawing few things. Let's say you have this point B here. So at this point B you have W acting and RB acting, and you have this MB also, but that is 0. Okay, we will initially take MB, but later on we will differentiate, then we will put it equal to 0. So this theta is 0. Then at this point here you have, use different colors. Here you have F theta, M theta, and again some different colors. Let's say you have this V theta. So let me first try to find out F theta. I'll have to balance the forces along theta direction. I have to write the forces along F theta direction. So if I write forces along F theta direction, so let me just find it out what are these directions. So if this angle is theta, so I can draw parallel lines actually, so passing through this point. And so let me just find it out. So this angle is 90 minus theta, and this will cast 90 degree on this line. Right? This yellow line will cast 90 degree on the purple line here, because this is 90 degree. This force is 90 degree for this line, and this line is parallel to this cross section. Anyway, so if this angle is theta, this is 90. This is 90 minus theta. This is This is 90 minus theta and this is 90, so this will be theta. And if this is theta, then this will also be theta. And if this is theta, so this is 90 minus theta. Sorry, this is 90, this is 90 minus theta. So this will be 90 minus theta. Okay. So this angle is 90 minus theta. So we can say that this angle with the horizontal will be theta. So we have theta here. Okay. If we have theta here with horizontal, this horizontal angle will also be theta. Right? Because these will be corresponding angles. If this will be theta, so we can say that this is 90 minus theta. This angle is 90 minus theta, and um, this angle again will be theta. Right? So now along f theta, what are the forces that you are able to see? So let me just write. Along f theta, so from here you will get um, RB cos theta, right? So once you have RB cos theta, at this point I'm saying, because at this point you have RB here, so RB cos theta will be along this line in this direction. So you have RB cos theta and what else? W. So for W, you have this 90 minus theta, so you have minus of W sin theta, because that will be pointing in reverse direction. Okay, and you have minus of f theta, so that should be 0. So basically I'm taking this direction as positive, and this I'm taking this as the positive direction and this as the negative direction. Okay, so in plus theta direction I'm taking positive, and in minus theta direction I'm taking negative. That's why finally I'm following the sign convention anyway. So that's why we are getting f theta, and f theta direction is towards this negative e theta direction only. So finally f theta you will get as RB cos theta minus W sin theta. So this is the axial force. Now you have to find shearing force. So let's say V theta. So you have to balance forces along this E theta direction. So V theta. So from RB you will get contribution in this direction, RB sin theta. So it's opposite to V theta. So I'm just writing as minus RB sin theta here. Then from W also you will get contribution. So W will be W of cos theta, I think. Yeah. So and that will be that will also be minus, because that is pointing in reverse direction to V theta. That should be equal to 0. So from here you will get V theta is equal to W cos theta plus RB sin theta. So RB sin theta plus W cos theta. Finally, we want to get the expression for M theta. So let's find it out. So we will balance the force about mm, about this point, let's say. So the moment due to f theta and v theta will go to 0, and the moment due to m theta is, let's say, positive because it's pointing in plus z direction. And due to rb, what will be the moment? So rb multiplied by, so this is the line of action of rb, and then multiplied by this distance here, right? So this distance will be how much? So you know that this total is the radius, and this is, so if this is the radius, this will be the radius. So this length here is, so this length here will be r cos theta, right? So this total, this left length will be r minus r cos theta, right? So the moment of rb will be also in plus z direction. So this will be plus of rb times r minus r cos theta, right? R is equal to a here, so that is equal to a. So I'll take return it is equal to a. Anyway, so now we have MB. So MB is um, pointing in which direction? That is in negative z direction. So I'm taking that as negative MB. and then due to W. So W, the line of friction of W is at a distance, this distance. So this is nothing but r sine theta. So, and that is pointing in plus z direction only. So that would be plus W r sine theta. R is equal to A. So I put, so finally m theta will be equal to mb minus rb into A. 1 minus cos theta. I have put r equal to A. 1 minus cos theta minus of W is sin theta. Right. So finally you have got this expression. Now the total energy. Now you just see here. These all are in principal direction because there is. Let me see. Okay. All three are perpendicular actually because if you see m theta, so that is pointing in plus z direction. If you see f theta, so that is pointing in minus e theta direction. And if you see v theta, that is pointing in er direction. So er, e theta, and ez, all three are perpendicular. So that's why these three are perpendicular to each other. So we can simply add them. There will not be uh, coupling between these three. So this is not, remember, this is not principle of superposition because these are usually perpendicular to each other, so there will not be any coupling between the components of these three forces or moments. So the total energy is given by, so that will be E and RB, FB and MB. So that will function of RB, FB and MB, I mean at the point B. So we have taken F theta and theta anyway. So from where, I mean, length will be 0 to 3 by 2 because 3 pi by 2 because angle is starting from here. So this is 0 and this is, we are going up to 3 pi by 2. Angle will be 0 to 3 pi by 2. So finally, the energy due to F theta will be F theta square over 2 EA. Energy due to V theta will be V theta square over 2 and shear correction vector and GA. And the energy due to M theta will be M theta square over 2 EI. And this will be d theta, right? And if you now put all the expressions, so finally, so you have 0 to 3 pi by 2. And if you put f theta, so f theta was rb cos theta minus w sin theta to the whole square and over 2EA. And if you put v theta, so v theta was rb sin theta plus w cos theta over 2 into shear correction vector into g into a, and this will be square plus energy due to this m theta. So m theta was mb minus w sin theta w into a into sin theta minus rb into a into a minus cos theta, the whole square divided by 2a. And then we have d theta. Just let me see. Actually, this will be not d theta, this will be ds. That is length along this structure. So that will be ds. And ds will be r d theta. Okay. Because the small length will be, let's say we are moving by angle d theta and radius is r, so arc length will be r d theta. So here we should write a d theta instead of a. So here it should be a d theta. Okay? Because we are integrating along the length. So that will be, small length will be a d theta. Anyway, so also we say that since there is no horizontal movement allowed at point B, so the horizontal deflection at point B, del Bx, that will be 0. Okay, in x direction at point B, the deflection will be 0. So we can say that it means del E by del RB, right? Because at point B, RB is the force in horizontal direction. So that should give del Bx, I mean the displacement in horizontal direction at point B, and that should be 0. If you differentiate this expression with respect to RB and put it equal to 0, so finally you will get 0 to 3 pi by 2. Here you have RB cos theta minus W sin theta. So over EA, and here you have cos theta, right? And plus here you have RB sin theta plus W cos theta over 2 will get cancelled into GA, and here you have sin theta plus MB, which you will substitute to 0 minus WA sin theta minus RBA 1 minus cos theta over EI, and this will be multiplied with um, A into 1 minus cos theta, and this is integrated from A to d theta, right? So now if you perform, and now you can substitute MB equal to 0 here in this expression, and now if you perform the integration, actually I'm making a mistake here, so here there will be one more minus because it is minus of RB. So once you will differentiate this expression with respect to RB, so you get minus of A times 1 minus cos theta. So now finally, if you integrate, so what will you get? You can try integrating. So I'm just writing the final expression of integration. So you have to integrate with respect to d theta. So if you integrate, finally you get A into A will be common, right? And you should put this equal to 0. Okay, this all should be equal to 0. And if you integrate, so what should you get? So this RB cos square theta is there, and then you should get cancelled with something here. If you simplify, you will get a very simple expression, not much difficult. Finally, you will get A times 3 pi RB minus 2W over 4EA. So for the first part, you will get this integration, and plus 3 pi RB plus 2W over 4K SGA. Actually, if you integrate this cos square theta from 0 to 3 pi by 2, so what should you get actually? So cos theta from 0 to pi by 2. Let me just see whether I can simplify this further or not. Cos theta 0 to pi by 2. So that will be sin theta. Sin pi by 2 is 1 side of 0. And this is fine. You should get 1. But it is square cos square theta. So area, okay, let me get last. So, actually, I need not to explain you. So, you already know the differentiation of cos square theta. So, cos square theta, you have to substitute as 1 plus cos 2 theta by 2. And then differentiation of 1 by 2 will be 3 pi by 2. So, you get 3 pi by 4 that we are getting here. and cos 2 theta by 2, that I think you will get 2. So that is coming here, 2 by 4, that is coming here. And the term with sin theta and cos theta, this will give you 0. Similarly, here sin square theta will give you this term, and the term with sin theta and cos theta. Just wait a minute. Yeah, actually it will not give you 0. So sin theta and cos theta you can write it as sin 2 theta by 2 and then integrate. Similarly here cos theta and sin theta you can write sin 2 theta by 2, and sin square theta you can write 1 minus cos 2 theta by 2 and then you can integrate. Similarly, if you integrate you will get these values. Okay. So you have to perform. So these are fairly simple trigonometric integrations you would have done already. So you have to do that. Finally, you should get this expression, which I'm writing here. RB into a square and 2 plus 9 pi by 4. Okay, and this should be equal to 0. And this if this is equal to 0, you can take RB as common, and then you will get 3 pi over 4EA plus 3 pi over 4 kappa GA plus A square and 2 plus 9 pi by 4. This term should be equal to W times, I'm taking all the W terms to other side, so 1 over 2 EA minus 1 over 2 kappa GA minus A square over 2 EI. So finally, you are getting RB as W times 1 over 2 EA minus, I mean, you should get this 1 over 2 kappa S, I mean, this is shear correction factor, 1 over 2 kappa SGA minus A square over 2 EI, and divided by, it should be divided by this term, 3 pi over 4 EA plus 3 pi over 4 kappa S GA plus A square into plus 9 pi by 4. Okay, so this is the final expression for arc. Please solve this integral, you should get this expression. Procedure is same. Once you have expression for RB, F theta and M theta, nothing is difficult. Now for finding vertical deflection, so vertical deflection at point V, right? So that is given by, tell me what will be the expression? So del at B, and that should be del E by del W, right? And if you do that, so finally you will get this thing, 0 to 3 pi by 2 F theta over EA del F theta by del W, right? Plus V theta over kappa S GA del V theta over del W, right? Plus M theta over EI and del M theta over del W. Right? And this should be equal to, I mean, this is AD theta. So del B, you can just write that 0 to 3 pi by 2. So F theta is RB cos theta minus W sin theta. And this is EA, and del F theta by del W, if you see, so F theta is this one, and del F theta by del W is minus of sin theta. Okay, so from here you can just put the value. So that will be minus of sin theta plus second expression is V theta. So you have R B sin theta plus W cos theta over kappa S into G into A, and del V theta by del W, so that is nothing but cos theta, okay, plus M theta over EI, so that is MB minus WA sin theta minus RBA 1 minus cos theta over EI, and that is A sin theta, and this whole thing will be multiplied with AD theta. Actually, del M theta by del W, so that will be A sin theta. You can see from here. That is minus of A sin theta, so I should include minus sign also. Here on minus sign will be there. Will be 0 plus of cos theta. And this is fine. Now, if you solve this, so firstly you have to put M equal to 0, because MB is 0. There's no moment acting at B, and you have the expression for RB as well. Now, you can further simplify this expression. So, and then you can integrate with respect to theta. You only have to integrate with respect to theta here. Theta is the only unknown. I mean, not unknown, but only a variable here. So I'll stop here for today. You can try to find delta B. You only have to integrate and substitute the value, substitute the expression for RB. You will get delta B. Similarly, in any other question, you have to find moments, axial forces and shear forces at any point in the cross section. Write down the energy and differentiate with respect to the force at a point at which you want to calculate deflection. Okay, so we will stop here for today and we will meet next week. Thank you for your attention.